All right, we're going to go ahead and just continue where we left off yesterday at we're right in the middle of number 20 here. But all we have to do is we've already taken our antiderivative, so all we have to do is plug in to our function. So we're doing f of b minus f of a. So we're plugging in our top number first. So we have, one sec. So we have 1/2 times -1 squared plus, I'm going to flip this. So u to the -1 is 1 over u. So my u is -1 on that one. Minus 1/2 times -2 squared plus 1 over -2. And then we're just going to go ahead and do that algebra. So -1 squared is 1. That gives me 1/2. This gives me -1. -2 squared is 4 times 1/2 is 2. Negated is -2. And then this is a negative 1/2 negated, which is positive 1/2. So 1/2 plus 1/2 is 1. So it cancels this one out. So we're left with -2. All right, number 21. Number 21 is just another one that we have to rewrite. Okay, so I'm going to do this. It's really a 1/2 right here. Okay, it's a constant multiple, and I'm just going to pull that out and deal with that in the end. Okay, so I still have the integral -8 to 8, but now I just have the cube root of x plus x. So I'm going to change that to x to the 1/3 plus x dx. Okay, you're allowed to pull out that 1/2 that's being multiplied by the whole function. If it's only being multiplied by one term, you would either have to split them up and then pull it out or just leave it in there. All right, so we leave that 1/2 there, and we're going to take our antiderivative. So I'm going to use a bracket this time. So add 1 to 1/3, and we get 4/3. So it's x to the 4/3. And then divide by 4/3, which means multiply by 3/4. And then the antiderivative of x is 1/2 x squared. And we're doing this from -8 to 8. Okay, so still leaving that 1/2 on the outside. And now we're going to do f of b minus f of a. So we're going to do 3/4 times 8 to the 4/3 plus 1/2 times 8 squared minus, you can put that in big parentheses, but you don't need to because everything's positive. Minus, now I need parentheses. I'm going to plug -8 in. So it's 3/4 times -8 to the 4/3 plus 1/2 times -8 squared. Kind of ran into the next problem there, but we'll be all right. All right, 8 to the 4/3. I would do the cube root of 8 first. The cube root of 8 is 2. 2 to the 4th is 16. And then 16 times 3/4 is going to give you 12. 8 squared is 64, and half of 64 is 32. Here we have the cube root of -8. Okay, we're going to do the cube root first. The cube root of -8 is -2. -2 to the 4th is 16. And 16 times 3/4 is still 12. But now it's a -12 because we got to distribute that negative in. And then this is also going to give me 32. And this is all going to cancel inside, and we're going to get 1/2 times 0, which is just 0. All right, questions? All right, number 22, the antiderivative of e to the x is e to the x. The antiderivative of 5 is 5x. And we're doing that, I don't know why I put parentheses around that, from -2 to 0. So we're going to have e to the 0 plus 5 times 0 minus e to the negative 2 plus 5 times negative 2. E to the 0 is 1. 5 times 0 is 0. This is e squared, but negated. And 5 times negative 2 is negative 10. Negated gives me positive 10. And combining like terms, you get 11 minus e squared. And we would leave it like that. That was supposed to be a negative 2, so this should be e to the negative 2. My bad. I only plugged in a positive 2 there. All right, questions? Some of you, I know, are going to need to be practicing those antiderivatives, so you need to go back and look at those rules. All right, let's go over to number 23. Do we know the antiderivative of an absolute value function? I give you a hint. It's either yes or no.
Negative.
We do not. Okay, we do not know the antiderivative of absolute value. Okay, it's not memorized. Okay, so when we don't know the antiderivative, we're either going to use a calculator, which we're not here, or we're going to draw the graph. Okay, so we draw the graph here. All right, so we're graphing the function, the absolute value of x minus 2 from 0 to 3. We should know from algebra that this is just the absolute value function shifted to the right 2 units. And it's going up like that, and it's going up like that. Okay, we want to know what our value be at when x is 0. So when we plug 0 in, 0 minus 2 is negative 2. The absolute value of negative 2 is 2. So that's going to be a value of 2 right there. And then when we plug in 3, we're going to get a 1. So don't look at my graph. It's not very accurate, but that's a 1. So the height of this triangle is 1. The height of this triangle is 2. So we just have 2 triangles there. We're going to add the areas of those 2 triangles up. So the area of this triangle is a base of 2, a height of 2, plus the area of this triangle is a base of 1, a height of 1. So that gives me 2 plus 1/2, which is 5 halves, or 2.5. Either one of those works. All right, number 24, same thing. We do not know the formula, or we do not know how to take the antiderivative of an absolute value function, but I want you to see this one because it can get tricky if you're not paying attention, okay? So I'm going to go ahead and just plug in my 2 numbers into this because I'm not exactly sure what that 2 is doing to the graph. It's going to be like a stretch, or it's going to be a stretch, but so we want to take a look at it. We're not exactly sure where all the points are on this. So when I plug negative 2 in, let's go ahead and plot negative 2 here. Okay, I get 2 times negative 2 is negative 4 plus 1 is negative 3, and the absolute value of negative 3 is positive 3. So at negative 2, I'm at positive 3. Okay, then I'm going to plug 0 in, and 2 times 0 is 0, plus 1 is 1. The absolute value of 1 is 1. So when x is 0, I get 1. Okay, and it would be not uncommon for someone to say that this is an absolute value function that goes like this, and it's going to look something like that. We don't know exactly where it turns, right? And then we would just say we're finding this area, which is a trapezoid. But that is false, okay? Because that is the vertex of this absolute value function is not over here, okay? It's actually on this side. So I'm going to go ahead and plug negative 1 in just so I can see where that point is. And when I plug negative 1 into my graph, 2 times negative 1 is negative 2, and negative 2 plus 1 is negative 1, okay? And so I get the absolute value negative 1 is 1. So I actually have a point here, okay? Now these are like side by side, right? Which means my vertex is actually down in here somewhere, and the vertex is actually at -1/2. Okay, we're trying to get 0. We want to find that vertex. We know it's somewhere in here. So at -1/2, 2 times -1/2 is -1. So I'm going to get a value of 0 here. Okay. Now, keep in mind, we're integrating from -2 to 0. So we have this graph that looks like this. So we need this triangle and we need this triangle right here. Okay, so that one was a little tricky as far as doing it without a calculator. Obviously, a calculator wouldn't matter what the graph looked like. All right, so first triangle right here is 1/2. The base is 2. And the height is 3. Plus this one is a base of 1/2 and a height of 1. Okay. Sorry, it's so tiny there. So 2 times 3 is 6. 1/2 of 6 is 3. And then this is going to be 1/4. So you could change this into 4. So you could call it 3.25. Or change that into a force. What would that be? 12 force? No, it wouldn't be 12 force. Yeah, it'd be 12 force, right? I feel like I did this math wrong. I did. This base is not 2. This base is 1.5. I called it 2. I was going all the way to 0. This base is 3/2. So this actually gives me 9/4 right here. So the final answer would be 10/4. Missed that one right there. Pay attention to that. Catch me if I'm falling asleep here. All right. So what we've done up to this point is we learned the fundamental theorem of calculus part 1, which says that the integral from a to b on f of x dx is equal to big F of b minus big F of a, or however you want to do the notation, doesn't really matter. But you take the antiderivative and you evaluate from b on b minus on a. Okay. Now we're going to actually start seeing the problems more in an application type process. Okay. And it looks something like this. Okay. You'll see questions that say, we're given this graph over here. Find the area of the region bounded by the graph of y equals 1 over x. That graph is graphed right here. Okay. And all this boundary stuff is just telling you what your lower limit, your upper limit is, and where you're shading. Okay. So we are bound by the x-axis. So we're not going to go below the x-axis here, okay? And the vertical lines, x equals 1. So this would be the line x equals 1, and the line x equals e, which is roughly 2.7, which is, we're just going to say it's right in here somewhere, okay? So I just want the area of this shape right here, okay? Obviously not a geometric formula for that because it's curving, okay? So we would do antiderivatives, or we would do the fundamental theorem of calculus part 1, okay? So the area is going to be equal to our lower limit, which is our left boundary, is 1. Our right boundary is e. Okay, remember this is at 1, this is at e. Okay, and it's the function 1 over x and then dx. Okay, if you don't remember, the antiderivative of 1 over x is the natural log of x from 1 to e. Then we're just going to plug in natural log of e minus natural log of 1. The natural log of e is 1, and the natural log of 1 is 0, and that's how we get an answer of 1. All right, so now we're going to give it a shot. Okay, so we're given this graph right here. It's the graph of 4 minus x squared, and we're bound by the x-axis and the line x equals -1, and obviously to the end of our graph right here. So we want this shaded region, and we're going to find the area of that. So we're going to integrate from -1, and then this value is +2. Okay, you can get that by finding an x-intercept on 4 minus x squared dx. All right, now it's we've written this. Now it's like all the examples we've been doing. Okay. The antiderivative of 4 is 4x. The antiderivative of x squared is negative 1/3 x cubed, or x cubed over 3, however you choose to write it, from negative 1 to 2. Okay, I'm not going to do all this algebra. Okay, at this point, you guys can plug this in. I'm just going to tell you that the final answer is 9. All right, number 26. Okay, we have the graph of cosine x, and it failed to state the line x equals pi over 2 here, but we are bound by the x-axis right here, and the line x equals negative pi, which is right here, and it should say the line x equals pi over 2, which is right here. So we want all of this area and all of this area right here. Okay, so we're going from negative pi to pi over 2 on cosine x dx. All right, so the antiderivative of cosine is sine. Okay, a lot of people are going to write negative sign there. Okay, negative sign is not the antiderivative of cosine, it's the derivative of cosine. Okay, so don't make that mistake. And we're going to evaluate that from negative pi to pi over 2. And again, I'm just going to tell you the answer is 1 on this one. All right, do I have any questions up to this point? All right, on the next couple of pages, oh, actually, we got 2 more up here. All right, so we don't have a graph this time, okay? But we could kind of sketch a graph. Well, we don't even need to sketch a graph. Here's all we need to know, okay? We're going to graph the function x cubed plus x, and it's going to be bound by x equals 0, okay? That's the y-axis. X equals 2, which is the x-axis, and y equals 0, which, excuse me, x equals 2, which is just a vertical line at 2, and y equals 0, which is the x-axis, okay? So we're going to integrate from our these are x values right here. So we're going to integrate from 0 to 2 on the function x cubed plus x dx. Okay, once again, okay, well, I'll find antiderivatives for you to give you that practice, and then I'll just tell you the answer. All right, the antiderivative of x cubed is, add 1 to that, you get 4, and divide by 4, so it's 1/4 x to the 4th. The antiderivative of x is 1/2 x squared, and we're evaluating that from 0 to 2. And you end up with an answer of 6. All right, number 9, we're bound by the lines x equals 1, x equals 9, and y equals 0. So this is the x-axis, and it's between our x-axis and our function. Remember, we have to change this because we do not know the antiderivative of square root of x. So we change this to be x to the 1/2 plus 3. So we're going to integrate from 1 to 9, x to the 1/2 plus 3 dx. Okay, the antiderivative of x to the 1/2 is, add 1 to this and you get x to the 3/2. Divide by 3/2, which means multiply by 2/3. The antiderivative of 3 is 3x, and we're evaluating that from 1 to 9. And this final answer would be 1/24 if you had a calculator. Well, I mean, if you had a calculator, you wouldn't even be doing this by hand, but if you had a calculator, you could turn that into a decimal. All right, now we have some just things. This is just explaining just some notation, really. This is the fundamental theorem of calculus, part 1 right here, okay? And it's just stating that this is little f, that's my function. And I'm taking the antiderivative of that and I'm getting capital F for this, okay? This is just would be the antiderivative. F would be the antiderivative, big F would be the antiderivative of little f, okay? Then they just kind of just said, but that really just means this, okay? Because we're taking, this is a derivative and we're taking the antiderivative to get back to the, let's just say position function, okay? That's just one example, okay? So if this is F prime, capital F prime, then this could be capital F and capital F, okay? This is just saying some notation. Really doesn't mean anything. But what's important here is this, integrating a rate of change, because typically this is going to be a rate of change, right? Okay, because it's the derivative of our original function, okay? And the derivative would be a rate of change, okay? So integrating a rate of change function, F prime over an interval, gives the total change in F over that same interval. Because say that's important right there. And we have done some problems, okay, where like we did the car problem, right? And when we integrated that velocity, we got the total distance traveled, okay, right? So the velocity graph is the rate of change, okay, of the position function, okay? All right, so here are just two examples. I'm just going to quickly run through them, okay? So the first one, and these are going to be like typical FRQ type questions that you're going to see, and there will be other stuff that you would be asked about this, okay, other than just finding a total here. But this is just step one of like your FRQs. So we have a chemical flows into a storage tank at a rate of C prime of T equals 180 plus 3T liters per minute, okay? So you just picture just like, you don't even have to picture a chemical going into a storage tank. You could just picture water going into your bathtub or filling up your sink, right? You're going to see these types of problems over and over again. Don't worry about really the scenario, right? It's just something's getting filled up. Okay. Eventually, we're going to get to the point where something is going in at the same time something is going out. Okay. And the rates would be different. And then how much is in at a certain time. Okay. So, liters per minute. T is the time in minutes. Okay. Find the amount of chemical that flows into the tank during the first 20 minutes. Okay. So we need to integrate this rate function. Okay. And that's what it said on the last page to get a total amount. Okay. When we integrate a rate, we get a total amount. The question is find the total amount of the chemical. Okay. So we're integrating during the first 20 minutes. So it's from 0 to 20 of our function C prime of T dt. And you could read through the rest of the actual antiderivative and then evaluating, and you get 4,200 liters of chemical flowed into the tank in the first 20 minutes. Okay, it's not a linear function of, actually it is a linear function flowing in the rate, okay? Not always will be a linear function. All right, in C, just another example, okay? So we're just trying to give you examples. Everything, although we use it a lot when we use position, velocity, and acceleration, we use those very often, but it doesn't mean that those are the only examples. But here's another one. Velocity of a car is given by this function. Calculate the distance traveled. That's the total distance traveled from time 1 to 4. So you're going to integrate from 1 to 4, the velocity function, which is the rate of change function, which is the same thing as doing S of 4 minus S of 1, which is the position at 4 minus the position at 1. Okay. And we integrate that. Okay. We get our position function and then we evaluate from 1 to 4. Okay. And it went 78 miles total distance. All right. So we did a car problem yesterday. So it's the same thing. All right. So just got a bunch of word problems. Okay. The key is don't freak out on word problems, right? You just got to pick out the information you need and put it into either an integral or a derivative. Okay. The rate of production for a new motorcycle. So we're just producing motorcycles. Okay. But this is a rate. Okay. So that is my rate function right there. I want to take the antiderivative of that to get the total amount. Okay. So the rate at which bikes are being produced is given by this function, T weeks after initial production begins. Write the integral, but do not solve. And the number of motorcycles produced in the first 5 weeks. So we're going to integrate from 0 to 5 that function. So 100 times t over t plus 10 squared, and make sure you're picking the right variable here, would be dt. Okay, it told us not to solve that one, so we'll just stop there. Any questions on how we're writing these? Okay, from here on out, we're just going to solve them, but again, it's been doing what we're doing, so we're just really going to interpret them. Okay. Suppose the rate at which ice in a pond is melting is given by this. Okay, this is a rate function. When we integrate a rate function, we get a total amount, where V is the volume of ice in cubic feet and T is the time in minutes. Find the amount of ice that has melted in the first 4 minutes. Integrating from 0 to 4, the rate at which it's melting. So that's 4T plus 2 dt. Okay, so the antiderivative of this is 2t squared plus 2t from 0 to 4. And I'm just going to tell you that answer is 40. Okay, the bigger question is the antiderivative, if we're good on the antiderivative. Again, I'm just using the power rule. Add 1 to the exponent, divide by new exponent. All right, 31. The sales of a company are expected to grow at a rate of, okay, where S is the sales in dollars and T is the time in days. Find the accumulated sales. That's the total amount of sales, okay? When we integrate a rate, we get a total, okay? Every time we're just doing the same thing in the first 5 days. So 0 to 5, 20 e to the t dt. All right, this one's a good one because the antiderivative of 20 e to the t is 20 e to the t. And we're going to evaluate that from 0 to 5. This one we could actually finish really quickly. It'd be 20 e to the 5 minus 20 e to the 0. E to the 0 is 1, so this would be minus. I didn't mean to put an equals there. Minus 20. All right, one more. Okay, in a memory experiment, the rate of memorization is given by m prime of t, where m is the number of words memorized and t is the time in minutes. How many words are memorized in 8 minutes? That's a total amount again, okay? Kind of trying to drill this into your head, I think, right? All right, in the first 8 minutes. So we're integrating from 0 to 8, 2 minus 3 over 1,000 t squared dt. Okay, and it actually says you can use your calculator after you find the antiderivative, okay, because the math is not going to be easy, the algebra, but we'll just find the antiderivative. So the antiderivative of 2 is 2t. Okay, the antiderivative, this is, don't freak out because it's 3/1000ths, okay? It's just a number. First, we're going to add 1 to this exponent, so we're going to get t to the third, and we're going to divide our coefficient by that 3. Okay, dividing by 3 means multiplying by 1/3, so off to the side, it would just be 3/1000ths times 1/3, and the 3's would cancel, so you're just going to get 1/1000th here, and evaluate that from 0 to 8. And it's saying now you can use your calculator to get that answer. I'm going to tell you it's 15.488 words. Okay, do I have any questions on setting up the integrals, antiderivatives, or actually using the fundamental theorem of calculus?
Can you show how to put that one in the calculator, please?
Yeah.
Like antiderivative?
Right. Oh no. Well, no, we're not doing the antiderivative in the calculator. We're just evaluating in the calculator. So you're just plugging in 8 into this and then 0 into this. So you would just be doing 2 times 8 minus 1 over 1,008 cubed, right? And then minus plugging a 0 in, but when I plug 0 in, I get 0, right? Okay, that'd be 0, that'd be 0. So it's just putting that into the calculator. the algebra.
Okay, thank you.
We're not really learning how to do the antiderivatives in the calculator till tomorrow. Tomorrow's lesson will be the antiderivatives in the calculator. Okay. So when we get to the test, okay, obviously you guys got to police yourself on Wednesday. And when I have a non-calculator section, you're going to have to show all of this work, right? And if you don't show all this work, I'm just going to mark the whole thing wrong. Okay. On the non-calculator section, because after tomorrow, you're going to know exactly how to type these into the calculator. Okay. And we kind of went through it a little bit yesterday, but we'll go through it more tomorrow. But you're going to have to show work on the test. Okay. If it's a calculator problem, no, not a big deal. You're just going to put answers down. But on non-calculator, I'm going to need to see all the antiderivative actually worked out and all that. Okay. All right. Any other questions?
So the net change theory, is this the fundamental theorem of calculus with f prime instead of f?
Well, yeah, it's just what you have to understand is all these other ones. Okay, so like let's just go back to any one of these problems right here. Okay, this we're taking the antiderivative of this, which means this is the derivative of some other function. That other function is 2t to the 3/2 in this case. Okay, but all that notation was saying is this is f prime. Okay, we don't have to call it f prime. Like when we're writing this out, we can call it f. But if we're going to call the function inside the integral f, then we can't call this little, and we're calling this little f. We just can't call this little f. We could call it big F. Or we could call this in here f prime, and then this is just f, big F, and big F. It don't get wrapped up into what we're calling it in there. This is the derivative of something. We're taking the antiderivative of it. And when you take the antiderivative of a rate, right, because a derivative is a rate, when you take the antiderivative of a rate, you're getting a total or an accumulation of whatever the function is, accumulating. Okay, does that make sense, Norris?
Yeah.
All right. Everybody welcome Norris today. He's normally in 6th period, but he's here today to join us. All right, any other questions? All right, guys, the homework is posted. It's not a worksheet this time. It's out of the book, but I posted the pages for you on there. It's just doing antiderivatives and evaluating, okay? And there's a couple of word problems thrown in there at the end, but some of them are just like these basic ones like this, all right? Have a great day, and I will see you tomorrow.
Have a good one.
Thanks, Norris.